Time is yours.
Okay, so today, as Felipe was saying, is the last lecture. And so the idea is to present some similarities of the configurations, the topologically non-trivial configuration that we have been studying in gauge theories, applications thereof in the context of anomalies. But today we will see how these configurations appear in gravity theories. Okay, in particular, I will focus on Einstein gravity with negative cosmological constant, and I will present some very nice features that these these configurations have. Okay. So what we have learned so far is that instantons are topologically non-trivial configurations. So they are labeled by different topological numbers, like the Chertoff-Triangle index. And so we have configurations which can be deformed one into each other if they belong to the same homotopy class. So if you have a particular configuration whose topological index is, let's say, 0, this one can be continuously deformed into the trivial vacuum, which is, let's say, a pure gauge configuration. But if you have another one which has a different topological number, then these two cannot be deformed continuously, one into the other. Instantons allows you to have tunneling between these two topologically inequivalent vacua. This is what happened actually in gauge theories. And indeed, since gravity in Euclidean signature can be thought of as a gauge theory for the SO4 group, then it is natural to ask whether these configurations exist in gravity theories as well. And we will see today that there are a lot of very similar properties that we have been studying during these two lectures that appears also in general relativity, namely some of these configurations saturate a sort of VBS bound, as we saw on Monday. You can integrate the Einstein field equations for a self-duality condition in a different sense that I will explain today. And this self-duality condition actually implies the Einstein field equations. So in principle, there is no need to solve the Einstein field equations. You just impose that your configuration is self-dual, and so the Einstein field equations are automatically satisfied. If I have enough time, I will discuss a particular gravitational instanton today, which is the self-dual tau-nat ADS solution, which is kind of a dion in a gravitational sense. And hopefully I can show some holographic features of this solution, okay? If not, I promise that you will have my notes and you will see these results there, okay? So today, gravitational instantons in ADS. Einstein ADS, okay? So to start with, we need to define an action principle, and this action principle, of course, is the action principle of general relativity. So the action, and I will be working in Euclidean signature during the whole lecture, okay? The action of Einstein ADS gravity in D equal 4 can be written in this way. So here I will define kappa. This is the integration on a 4-dimensional manifold. Square root of G R plus 6 L squared. And in general, there will be here boundary terms. Where kappa is proportional to the inverse Newton constant, the cosmological constant, and the ADS radius are related in the standard way for D. And this G, of course, is the determinant of the metric. Okay? So you know that solutions to Einstein field equations, even without the cosmological constant, doesn't satisfy a variational principle in general. Because when you vary the bulk action, there will appear boundary terms that depends on normal derivatives of the metric that cannot be demanded to be zero by imposing Dirichlet boundary conditions. Okay, so the standard idea that Gibbons, Hawking, and York proposed is to add an extrinsic boundary term that is indeed the trace of the extrinsic curvature, such that the normal derivatives of the boundary metric are cancelled by variations of the Gibbons, Hawking, York term. Besides that, in ADS, there appears infinities. Infinities when you integrate in the whole space, and these infinities have to do with the fact that the boundary, the proper volume of ADS is in general divergent. So we need to introduce counter terms to cancel these divergences, and also these divergences will appear in variations of the action as well. So they appear at the level of the action and also at variations thereof. So besides the standard Gibbons, Hawking, York term that you need to adhere, you need to put boundary counter terms. And there are different proposals in the literature. Some of them are constructed out of intrinsic quantities, like the one proposed by Barasura, Maner, and Krauss, or Embark and Johnson-Myers, and later on Skenderis and collaborators, De Haas and other people gave a super systematic way to find these counter terms in whatever theory you want. I will be considering another kind of counter terms during this talk, okay? That I will mention in a moment. But first, it is convenient at this stage, since we are working in ADS gravity, it is convenient to define a displaced Riemann tensor, okay? That some people call it the ADS tensor. I will call it now displaced. Let us define the displaced Riemann tensor. I will call it with an F because it will be sort of the analog of the field strength in Yang-Mills theory, but it is an F with more indices than the field strength. And this guy will be the Riemann but displaced by a constant tensor. That is this generalized Kronecker delta. Are you guys familiar with this object? Some of you are not. So let me give some properties, because we will use these properties throughout this lecture. So in general, we can define the generalized Kronecker delta as a rank P tensor, which is completely antisymmetric, where, let's say, mu P mu P is just the antisymmetrized product of Kronecker deltas. Sorry. Okay, and actually, since it is the same object, the one that you are symmetrizing, you can see that it is exactly the same if you antisymmetrize the upper indices. Without antisymmetrizing the one below. Or the other way around. Symmetrizes the ones below without antisymmetrizing the one above. Okay? And there are very funny traces that you can take from this P. And it satisfies. If you take, for instance, you have P indices, and you contract K of them. Let's say mu 1, mu K, mu K. This will give you a factor that depends on the dimension, the numbers of the indices of the generalized delta that you're contracting, and the number of contractions. Okay, and this factor is minus P plus K factorial D minus P factorial, and then a generalized delta with the remaining indices. So this will be mu, let's say K plus 1 up to P, K plus 1 up to mu P. And of course, here we are considering that K P, lies in the following range. Okay? And we'll be using some of the properties of the delta in this talk. But there is a very nice way of writing the Einstein field equations that, of course, are obtained by performing stationary variations of the Einstein-Hilbert action with respect to the metric. And so if you do that, so arbitrary variations of the action yields. The boundary term won't contribute to the bulk dynamics of the metric, but of course will change the finite value of the action and also their variations, okay? But the field equations that I will define with this tensor can be written in this way. The standard Einstein equations with the cosmological constant, with a negative one, of course, union. But notice that the Einstein equations can be written in this way. Minus 1 over 4 delta mu nu alpha beta gamma delta r gamma delta alpha beta plus 1 over L squared gamma delta alpha beta. Let me convince you that this is what you get, and this will be in terms of f, this will be minus 1 over 4 delta mu alpha beta gamma delta f gamma delta alpha beta. Since, let us take the first piece, okay? So the first piece, well, let us do it all at once. You can decompose this, since it is the antisymmetrized product of deltas. I can take this in the following way. So I will take a delta here and put an antisymmetrized delta there, gamma delta plus, and then I will perform cyclic permutations in the indices below. So this will be gamma here, sorry, delta here, mu gamma plus gamma delta mu alpha beta mu alpha beta times this guy, gamma delta alpha beta alpha beta. I will perform the contraction only of these deltas with the Riemann, because the other one, the delta 3 with the delta 2, I will use the property above, okay, because otherwise it is too long. But the interesting thing is that this contraction with this guy is the Einstein tensor. Okay, let me show you that. So this is equal to minus 1 over 4. This guy is 2 times the product of 2 deltas antisymmetrized in the indices, but these indices, let me put it in this way, so this is 2 times delta gamma delta alpha beta, but the Riemann is antisymmetric in gamma delta, so I can remove the brackets here, and that will give you alpha beta contracted with gamma delta, so this is the Ricci scalar with a factor of 2. And notice now this same thing here. This guy is 2 times delta alpha, beta, nu, gamma. So this will be alpha, beta, then I need to change this by nu gamma, but there is a contraction with gamma here, and then I need to change delta by mu, and so this will be, I need to change, because notice that gamma is here, and then gamma is in the other index, and when delta goes here, it gives me a mu, so I need to change either here or here in order to get the Ricci tensor, so that will give me a minus, so this is a minus 2 r mu nu, and the same thing will happen here, okay? So take this is 2 times delta alpha beta delta nu. You do the same thing, this will give you r mu nu, and then you can see that this is the Einstein tensor. And now let me perform the other one. I will just take minus 1 over 4 delta mu alpha beta nu gamma delta, and this guy goes with this one. So I have 4L squared, and I will put a factor of 2, because notice that it is contracted with this, that it is antisymmetric in alpha beta, so this delta. So I can remove the brackets. I have a factor of 2 here. This will give me delta gamma, delta alpha, and beta. Okay? So I will continue here. So this is equal to, now I will take this, will give me minus 4. So this is the Ricci tensor. The other one is minus 1/2 delta mu r. And let us work out the last term. So this is minus 1 over 2L squared. And now we are working in 4D. The rank of the delta is 3, and it is contracted with 2 deltas. So this will give me the dimension is 4. I'm using the identity above. The rank of the delta is 3, and I'm contracting with 2 indices, with 2 deltas. So I have this one, and then 4 minus 3 factorial delta mu nu. And so this is 3 factorial that cancelled with this. So this is r mu nu minus 1/2 the mu r minus 3 over L squared delta mu. And writing the Einstein field equations in this way is super convenient for what I will show, because we can demand self-duality at the level of this F, and due to Bianchi identities, we will see that the Einstein field equations are automatically satisfied. I will do that later, okay? But just to remind you that this is equivalent, the Einstein field equations with negative cosmological constant is equivalent of writing it in this way.
But
Yeah.
this happens in every dimension, or is a particular thing in dimension 4?
It happens in every dimension. Actually, the only thing that will change is the factor here, because there is a relation between lambda and the ADS radius that depends on the dimension, but it will give you the correct factor here, such that the Riemann can be written in this way in every dimension. So actually, if you plug this and you take arbitrary dimensions there, you will have actually the relation between the cosmological constant and the ADS radius in general. So just take here D, and then you will have the Einstein field equations in arbitrary dimensions.
The D minus 1 over...
Exactly. This is what you will get. But it goes in every dimension. Okay? Any other question? Okay, so if the Einstein, notice that this is a tensor. This is not an equation yet. The equation will be this equal to 0. If this is equal to 0, of course, I can take the trace. I can take the trace on both sides. And then you will get the Ricci scalar that will be minus 12 over L squared. You plug it back there, and then you will have the trace reversed Einstein field equations, which are just this. This will be minus 3 over L squared. And so all Einstein spaces satisfy this condition, that the Ricci tensor is proportional to the metric, in this case to the delta. Okay? And this implies that you can write the bitensor in terms of this displaced Riemann tensor we have above. Okay, so if you perform the reducible decomposition of the Riemann tensor, you know that the Riemann can be decomposed into its trace, into its partial traceless part, and in terms of its completely traceless part, which is the bitensor. And in dimension 4, is the following. This is the bitensor plus factor of 2 delta mu h mu. I will tell you in a moment what h is. Lambda rho plus 1 over 12 delta mu lambda rho and the Ricci tensor. In this case, this guy h where h is the traceless Ricci. In 4 dimensions, there is a 1/4 here, so it is not the Einstein tensor, of course, because you have a 1/4. Okay? And it is, of course, direct to see that this guy is traceless. H is traceless. But moreover, there is a very important thing, is that H is identically 0 if you evaluate this guy in Einstein spaces. So if you plug, this is an exercise that you can do now in 2 lines. If you plug this here, you will see that H is identically 0. And so, if you consider now this part where we have obtained the Ricci scalar from here, we can see that for Einstein spaces, this is general. I'm not assuming anything at this level. But if you now assume that your space satisfies the Einstein field equations, then this will vanish. R now will be minus 12 over L squared. And the Weil tensor will be R minimum. Notice that this 1 over 12 will cancel with the 12 there, and there is a minus, but I will put it on the left-hand side, so it goes with a plus. And this is delta mu lambda rho, which is exactly the displaced Riemann tensor I defined above. Okay? So, on shell, the Weil tensor evaluated on Einstein spaces, which of course satisfy the Einstein field equations, so the Weil tensor will be exactly the displaced Riemann tensor. Another thing, do you recall what the Weil tensor for global ADS space is? What is the Weil tensor of global ADS? You recall that, guys? The Weil tensor is 0 because ADS is conformally flat. And notice that written in this way, the displaced Riemann tensor, as I was saying before, it is sort of a measure of the curvature with respect to a maximally symmetric space with negative curvature. And if you evaluate the global ADS space, which is an Einstein space, of course, and you evaluate it here, since global ADS is of constant curvature, but with negative constant curvature, so the Riemann will be exactly minus this guy. So they will cancel each other, and you will see that the Weil tensor for global ADS is 0. Okay? And it makes sense when you compare it with the displaced Riemann tensor, since we are measuring how the curvature is with respect to a maximally symmetric space. And since ADS is a maximally symmetric space, the displaced Riemann tensor will be 0. Okay? All right. Any questions so far? Okay. Now let us go to the issue of renormalization of the Einstein ADS action. Oh, sorry, you have to. Did you take a picture or something, or did you take notes? Yeah. Okay. Take the picture. Okay, so let us come back to the action for a moment. And notice that in general, if we evaluate the action on shell, And this is different to what happens in the case of Einstein-Hilbert without the cosmological constant, because if the cosmological constant is absent, it is equivalent of taking the limit of infinite alias radius. So the Ricci tensor is 0 and the Ricci scalar is 0. And so the action, you will see that it is composed only by the first term. And since the Ricci scalar is 0, the bulk action will be 0 as well. And the whole contribution of the action to the partition function, as Professor Castro was explaining yesterday, in that case, all the contribution will come from the boundary terms. But in the case, if you have a cosmological constant, the bulk action is not necessarily 0. And actually, it is divergent. Because if you evaluate now, d for x, the square root of g. And now we take the value of the Ricci scalar, that in this case was minus 12 over L squared. Now we have a plus 6 over L squared here, plus E boundary and in general this guy will be proportional to the volume element, and then you need to integrate, and that integral is divergent. So E on shell, okay, I will take out the minus 6. Minus 6 k over L squared d for x square root of g. And this is it, plus the boundary term. But in ATS, this guy is divergent. So we need to choose wisely the boundary term such that these divergences are cancelled. Okay? And there are different ways of doing that. As I was mentioning, there is a prescription done by the people at the end of the 90s by including intrinsic quantities in the boundary term such that they cancel the divergences. But there is another possibility of including topological terms. And this was done by people here in Chile, by Rodrigo Aros, Rodrigo Lea, Troncoso, Zanelli, and the people at SEX. Also at the end of the 90s, and it is very convenient because it is related to the Gauss-Bonnet theorem, and it is actually a bulk term that you can add that doesn't contribute to the field equations, but it does modify the value of the action and variations thereof, rendering this action finite for asymptotically locally ATS spaces. And the nice thing is that since it can be written as a bulk term, it is covariant. So if you would like to compute conserved charges, for instance, it gets adapted to every codimension 1 surface that you would like to consider. So in this sense, will be convenient for some of the things that I would like to talk today. And this is called topological renormalization by Aros, Olea, Troncoso, Zanelli. Then also Libera was working on this, and other people as well. But Rodrigo Lea is one of the guys that have been working on this the last year, and is expert on the topic. And the idea is to consider, instead of intrinsic boundary terms, you can consider extrinsic boundary terms, like the term form. And the term form is something that appears in the Gauss-Bonnet theorem. Consider the Gauss-Bonnet theorem in 4D. And the idea is that you can relate two integrals. One is a bulk integral, and another one is a codimension 1 integral. And these two are related with a topological invariant, which is called the Euler characteristic, plus 4 m d3x square root of h. H is the induced metric on the codimension 1 boundary. And here you have d mu alpha lambda rho beta k lambda mu. This curly R is the intrinsic curvature associated with H. It's the curvature of H. Okay? With the 1/2 rho beta mu alpha plus 1/3 k minus rho k beta mu alpha. And this is what the people usually call the Chern form. This is the Gauss-Bonnet. Is r squared minus 4 mu plus lambda rho. And this is a topological invariant of the Euler class. It is the Euler characteristic. And in 2 dimensions, you know that this guy measures, you have a manifold which has, let's say, some boundaries, but it also have some holes. These are genus and these are boundaries. So the Euler characteristic of this manifold give you 2, put it here, 2 minus 2 genus. Genus is the number of holes. Plus or minus, Borja? I always forget this. Okay, plus or minus, let's say, plus the number of boundaries. Okay? So it doesn't depend on the metric itself. Actually, it depends only on the topology. It is a topological invariant. And it is related with these kind of things. Actually, if you have a dia at the 2012 or something, included also the contributions coming from conical singularities or simply connected or non-simply connected parts. So the Euler characteristic counts all these topological features of your manifold. K, so H, continue now. Here, H is the induced metric. And so in order to define an induced metric, I need a normal vector. And K is the extrinsic curvature. So, and H mu is G mu minus N mu, and of course is the normal, the unit normal, I'm working in the Euclidean, so all my vectors are space-like. So there is no need to specify whether this guy is space-like or time-like. It's the unit normal to M. I forgot to, I don't know, the M is there. And K mu is H mu lambda and mu. So this is the extrinsic curvature, and the curly R is the intrinsic curvature. That it can be defined, of course, as the curvature of H, but you can define it as in terms of the Gauss-Codazzi equations, which are, this is the standard Riemann tensor, alpha, beta, gamma, delta. So I have to put here mu alpha, mu beta, H lambda, H rho, gamma, delta, plus 2 times K lambda rho mu. Okay. This is all that I need. And the idea is that you can convince yourself that actually the Gauss-Bonnet or the transform both are divergent in ADS spaces. Of course, their sum will give you something finite, that it is the Euler characteristic. But the Gauss-Bonnet by itself is divergent in asymptotically ADS spaces, and it doesn't contribute to the field equations, so it can be regarded as a counter term. So actually, you can use either the Gauss-Bonnet or the transform, because adding whichever you want of these two is equivalent up to the Euler characteristic. So at the most, your action will change by a constant. And since the Gauss-Bonnet is a bulk term, and it will allow me to have covariant quantities, conserved quantities, for the sake of simplicity, I will use now the Gauss-Bonnet as a counter term. And so the idea of topological renormalization is to add to the action the Gauss-Bonnet term. I can use an arbitrary constant in front of the Gauss-Bonnet because it won't modify the field equations. But now I need a criteria to fix alpha. And the criteria in this case will be the finiteness of the action when I evaluate it on asymptotically ADS spaces. And then you will see, even actually you can plug global ADS here, and since global ADS can be regarded as the ground state of Einstein ADS theory, we should expect that the action has to be zero. In order for that thing to happen, alpha has to be fixed to be then renormalization on asymptotically locally ADS spaces. Fix alpha in this way over 4. And this is super nice because you can play around with the delta, with the properties of the generalized delta, and you can write the Einstein-Hilbert action with the Gauss-Bonnet in a very funny way. Yeah.
Does the Gauss-Bonnet term is invariant up to Bayesian formation diffuse, or you get a boundary term when you do a Bayesian formation?
It is invariant under diffuse. Invariant, because all the indices are contracted in this case. Yeah, so it is invariant in general.
It's not like Chern-Simons, but you get a boundary term.
It is not like Chern-Simons, but because you can consider another topological invariant that I will talk about in a moment, like the Pontryagin density, but the Pontryagin density is also an invariant. The thing is that these guys can be written locally as a boundary term. It is what if you use differential forms, you can write the Gauss-Bonnet is proportional to epsilon A, B, C, D, R, A, B, wedge, R, C, D, and then you will see that this guy, the G is proportional to this. But then you can see, also playing around with Bianchi identities and so on and so forth, that you can write this as the exterior derivative of something that I will call CE. This is the Chern form associated to this guy, that then you can see that it is related to the last codimension 1 integral I wrote above.
Okay.
And this guy is not gauge invariant, but it is quasi-gauge invariant in the sense that under diffuse will transform as a boundary term. The same will happen with the Pontryagin density, that it is another topological invariant that I will talk about in a moment. You can also write it in this way, so then you don't put the epsilon here, you just put R wedge R, and you contract the indices. This is also a topological invariant, can be written locally as a boundary term. And the Chern form, the Chern-Simons form in that case, will endow the same properties as the Chern form. Namely, it is not invariant under diffuse, but it is quasi-invariant. It will transform as a boundary term.
So you get the large diffuse, get you a different contribution, right?
If you are considering this as a Lagrangian, this is true, you will get that one. But I'm not using this, I'm using this, and this guy is invariant, actually. And this can be seen as follows, because if this transforms as a boundary term, then you will have an exterior derivative acting twice. This will be zero in general. But if you consider this alone in one dimension less, as a possible Lagrangian, which you can do that. Actually, it's an interesting term that you can consider in 3D. This guy will give you contributions to the if your theory in one dimension less has boundaries. Okay. Now, if you use that and use the properties of the generalized Kronecker delta, we can write then the action can be written as, and this is renormalized, so Einstein-Hilbert action renormalized, this will be k L to the quartic over 16 d for x square root of g delta nu lambda rho alpha beta gamma delta r alpha beta mu plus 1 over L squared mu alpha beta r lambda rho gamma delta plus 1 over L squared delta lambda rho gamma delta. And I'm not assuming that this is that the action is evaluated on Einstein spaces. This is completely general. And at first sight, you see this and oh, this doesn't look pretty much as the Einstein-Hilbert action. But actually, you can use the properties of the generalized Kronecker delta, and you will see that it is exactly this, with alpha being L to the quartic over 4. So it is the Einstein-Hilbert action plus a bulk term that can be written as a boundary term using the Gauss-Bonnet theorem. And now the funny thing is that this guy, as we were saying, looks pretty much, it is the definition of the displaced Riemann tensor. Mu1, mu4, mu1, mu4, and this will be F mu1, mu2, mu3, mu4, mu1, mu2, mu3, mu4. So it is quadratic in F. So it looks pretty much as the Yang-Mills action, but for another group in this case. So, what about self-duality in this case? But before going to self-duality, I would like to introduce another invariant. But before that, notice that in general, for Einstein spaces, so on shell, this is for Einstein spaces, ADS spaces, we demonstrated that F is equal to the y. And so, and the y is completely traceless. And so, if you expand the deltas and take all the possible contractions with the F, that on shell the F is the y, you will see after expanding the delta, there will be a +4 that will cancel this 16. There will be a 4 here. So this is on shell. D for x square root of g. This will be by squared. So on shell, topologically renormalized Einstein ADS theory is sort of equivalent to the action of conformal gravity. Okay? And this action you can show that it is finite. Plug your favorite solution, your favorite ADS solution, or asymptotically ADS solution, charge at ADS, or whatever asymptotically ADS solution you want, and you will see that this is finite. And notice that for ADS, for global ADS, as I was saying, the value tensor is 0, so you can check in one line that the action is 0 as well for global ADS spaces. So we have set ADS as the ground state in this case, such that the action is 0 once evaluated on global ADS spaces. Okay? And in this way you will get finite action, and also I'm not going to talk about now about conserved charges. But you will get also finite conserved charges as well using this method. Yeah.
So this is binding variant, right? You can do a base transformation.
Yes.
What's the charge that you get from there? What is the meaning of that charge?
Depends on the method you use, but you can, for instance, you can take the Nether-Wald formalism, and then, which is nice because it is covariant in the way. So if you compute the Nether potential, plug it into the Nether-Wald charge, you will get exactly the same result as ADT method for computing the mass of your black hole.
Oh.
Yeah. And actually, it coincides with other methods, like if you would like to use the renormalized quasi-local stress energy tensor of Balasubramanian-Krauss, which is the improvement of the Brown-York tensor for ADS spaces, you will get exactly the same charges using this method. If you would like to use another one, like Ashtekar-Mayon does, that it is super well adapted to asymptotically ADS spaces, you will get exactly the same charges with this method. The nice thing is that this one is covariant, so it is far more convenient when you are considering not more than one codimension one hypersurface to integrate that.
If you do linearized gravity around this theory, the linearized theory is also very conformal invariant. The deformation, the H-mu deformation.
This is something that I don't know. This is a good question. I would expect that because at least considering Einstein spaces, the theory that you end up with is conformal invariant, as you can see from here. But I haven't studied perturbations in this stuff, but it is a good question. Okay, so we have some nice similarities using this method with Yang-Mills theory. So is it true that demanding self-duality, we will solve the Einstein field equations at once? Let us see that. So we have a Yang-Mills-like action now for the ADS curvature. So let us see if we can use the self-duality trick to solve the field equations. So anti-self-duality, self-duality in ADS gravity And since the object that is playing the role of the gauge field strength in this case is dF, the natural thing to do would be to demand that F is self-dual. Namely, F, let's put it with, okay, as you wish, plus minus F tilde lambda rho, where will be 1/2 alpha beta F alpha beta lambda rho. So this is the self-dual or anti-self-dual condition at the level of dF. And this is the definition of the dual. There are two different things. Okay? Now, let us see if we can solve the field equations automatically by imposing this. The field equations become, and I showed you at the beginning that the field equations can be written in this way: -1/4 delta mi alpha beta gamma delta F gamma delta alpha beta. But now we'll impose the self-duality condition, okay? So here, self or anti-self duality condition. So I have a minus, I will have then a minus plus 1/4 delta mi alpha beta nu gamma delta F tilde gamma delta alpha beta. And now we will replace the definition. So this is a condition, now I will replace the definition, all right? So this is minus plus 1/4 delta mi alpha beta mi gamma delta. And I think that at this point it's convenient to use the identity I used before. Namely, I will expand the delta and I will put delta mi delta alpha beta gamma delta plus, I put the delta in front, mi gamma plus delta gamma delta mi, and now mi alpha beta alpha beta. And now we will plug the definition of the dual F here. So this will give me 1/2 epsilon, gamma delta lambda rho, no. Have I used lambda rho? No. Lambda rho F lambda rho alpha beta. And now 1/4. All of them will give me a factor of 2 when I use the definition of the Kronecker delta, of the generalized Kronecker delta. So this is a factor of 2. And now here I have mini. And now alpha beta here will be gamma delta. So this will be epsilon gamma delta lambda rho F, lambda, rho, and alpha, beta are gamma, delta. Plus, then I have epsilon, the delta goes with a mu, and so I have gamma, mu, lambda, rho, and F, lambda, rho. But now alpha, beta are nu, gamma. And finally, epsilon, this is gamma, no, sorry, gamma now is mu. Then there is a delta, lambda, rho, and the F, alpha, beta now are delta, nu. Lambda, rho, delta, nu. But notice now, there is an epsilon, and I have lambda, rho, delta, gamma contracted here. I have Bianchi identity, because we know F has exactly the same symmetries as the Riemann. So we know from Bianchi identity, and recall what happened in the case of Yang-Mills. We were also using the Bianchi identities. So now, by virtue of the Bianchi identities, is there any question for running out of time? Yeah.
You said before, but does the duality condition depends on the range of the effective form and the dimension, right? Is dependent?
Sorry, say it again?
The duality condition is dependent on the dimension we're working at.
Yeah, good question.
The range. Yeah.
Good question. F is a two form. So in 4 dimensions, the dual maps two forms into two forms. So the self-duality condition at the level of F only works in 4D. If you are in higher dimensions, let's say in 6 dimensions, the only forms that will be self-dual are 3 forms. Because in 6D, 3 forms are mapped by the Hodge dual into 3 forms. In 8 dimensions will be 4 forms can be self-dual, so on and so forth. Always the middle of the dimension. Half of the dimension, I mean. You're welcome. So we have Bianchi identities, and notice now there is a contraction between all the indices of the epsilon that it is completely antisymmetric with all the indices of the F that it is antisymmetric as well. So this vanish due to Bianchi identities. Same here. Lambda rho gamma. Lambda rho gamma. 0 because of Bianchi. Same with the last term. So lambda rho delta. 0 because of Bianchi identity. So at the end of the day, if you take the Einstein field equations in the presence of the negative cosmological constant, and you assume a self-duality condition for the F, this automatically solves the Einstein field equations. And it is nice because what happened at the level of the renormalized action, recall that the renormalized action can be written as a kind of Yang-Mills theory for the ABS curvature. The renormalized on-shell action becomes So recall that this was k L2 L squared to the quartic Where 16 d for x square root of g delta mu1 d4 mu1 d4 f to f d4 d4. So if I evaluate this on anti-self dual f, this will give me a plus, minus, and I will change only one of these two. If I change the two, I will get exactly the same. So I will change only one. Felipe.
So the equation of motion does not give you any constraints on it?
No. The only thing that tells you the equations of motion is that they are automatically satisfied if f is self-dual. But if the field equations are satisfied, you know that f is identical to the Weich tensor. This is what you know. So now we have a relation between the f and the Weich tensor. And actually this is what I will use here, because if these guys are on-shell equivalent to the Weich tensor, but actually you don't need to use that at this point. You plane a little bit, you expand the delta in another way. You can see the details in my notes. You will see that this is plus minus k L4 4 d for x square root of g, and this will be f min lambda rho f tilde lambda rho min e. And now there is an identity that you can show using that f tilde is equal to r lambda rho r tilde lambda rho. Meaning this is an identity you don't need to use that these are Einstein spaces. This is an off-shell identity. So you use that here, and you will see that you get to the quadric over 4 d for x square root of g r tilde or r tilde lambda rho min e. And this is also a topological invariant of the Pontryagin class. This is the analog of the Pontryagin index in Yang-Mills theory, but now for gravity. And so you can define, this is upon some conventions, this can be written as plus minus 4 pi squared kappa L squared P1 of m. So the P1 of m is 1 over 16 pi squared over the square root of g. Which is also topological invariant. Felipe.
Now the thing is the
10 minutes?
Yes.
Okay, that's nice. So let me finish. Is there any questions so far?
So this is very similar to the Maxwell case that we did before. So in the Maxwell case, we will get that the instanton is a stealth mode of the
Yes.
stress tensor. One would expect that this happened for the holographic stress tensor here or something like that.
Good question. Actually, it does give you something, but you can modify. If you modify the action by adding a term like this, such that the action is zero once evaluated at anti-self-dual solution, what you get is exactly what you said. So the holographic stress tensor will be zero if you modify the action by adding an additional topological term. So notice that here the only topological term that we added was the Gauss-Bonnet term.
Yeah.
But actually, you can say, okay, I can add this another one into the action because it won't modify the field equations. But now I need a different criteria to choose the coupling of this topological invariant. In the case of the Gauss-Bonnet, our criteria was finiteness of the action. But now, this guy, in asymptotically locally ADS spaces, this guy doesn't contribute to divergences. This guy is finite. So you need a different criteria. It won't contribute to canceling divergences, but it will modify your action at a finite level. So a criteria that Rodrigo Olivera found in 2009 was to fix the coupling of the Pontryagin term such that the action is zero once evaluated on self-dual configurations. So you have the topological renormalized action plus a Pontryagin term of this form, and you can choose the theta term in front of the Pontryagin density such that this term is cancelled. The idea is the following. So you put this guy from scratch, then you will have contributions from this, and then you cook the parameter in front such that this term is cancelled.
And at the level of holography, adding topological charges, deforming the theory,
Yeah.
is
Will,
like adding topological charges in the CFT or something like that?
will change at the level of the holographic stress tensor. It will change the holographic stress tensor in a non-trivial way. Actually, if you fix that, the holographic stress tensor will be zero.
But you're deforming the CFT, right?
You're deforming the CFT, exactly. Yeah. All right, so let me give you an example of a particular solution that satisfies this, and then I will finish because I'm running out of time. And so the idea, I'm not going to solve the Einstein equations. Actually, I will impose self-duality condition at the level of the displaced Riemann tensor and see whether we can find a solution out of that, because we know that if the displaced Riemann tensor is self-dual, the Einstein field equations will be automatically satisfied. So let us assume this is the Euclidean tau naught ADS instanton. And so you're going to start. There is a long story that I'm not going to tell you about how the tau naught metric was found in the first place. If you are interested, I can tell you in the coffee break. But the idea now is to consider the following metric ansatz in the Euclidean section. Put here psi, okay? So if you impose this condition, that we know that will imply the field equations automatically. Let us do it only with the plus now, for the sake of simplicity. I will consider that one. Let me tell you another thing first about this metric. Recall from the first lecture, this can be written in terms of the left invariant forms of SU2. I can take now this guy outside, so I will put here, sorry guys, this is a tau. I will put the 2n outside, so this is f of r n squared, and I will perform a relabeling of this tau. So this should be the psi. Put it here. Psi is tau over 2n plus cos theta d phi squared plus blah 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 plus r squared minus n squared. And so this looks pretty much, this is sigma 3 squared. Sigma 3 of the left invariant forms that we were discussing on Monday. And this one is sigma 1 squared plus sigma 2 squared. So the nice thing is that the Euclidean tau metric can be written in the following way. Plus, I will take the area coordinate outside. N is a parameter, it is called the nut charge, and it plays the role of a gravitomagnetic charge. It is kind of, the tau nut metric is kind of a gravitational dione having a gravitoelectric source and a gravitomagnetic source, and the magnetic part is sourced by the nut charge itself. And now, but there is another very interesting interpretation of the nut charge. So you can factorize this with the area coordinate in front. This is sigma 1 squared plus sigma 2 squared plus, and now I have here the f of r for n squared, r squared minus n squared sigma 3 squared. And so notice that the hypersurfaces of constant radius looks as a 3-sphere, but with a squashing parameter here. So the boundary of the tau nut metric is actually a squashed sphere. And there are very interesting holographic applications in general for asymptotically locally ADS solutions whose boundary is non-conformally flat. Non-conformally flat in the sense of the cotton. So if you take hypersurfaces of constant R in this case, and you take the codimension 1 boundary of areas and compute the cotton tensor of this boundary metric, you will see that the cotton tensor is different from 0. And this is interesting because the people, when studying holography, have found very interesting applications of asymptotical EBS solutions having these kind of boundaries, like modeling holographic fluids with non-trivial vorticity, etc. But you can see that the squashing parameter is very much attached to the presence of the nut charge. So the nut charge is also playing the role of a squashing parameter of the boundary metric. Okay? All right, so let us impose now.
Sorry, no, listen.
Yes.
The n parameter that is related to the magnetic charge.
Yeah.
Is the same magnetic charge to obtain when you're integrating in minus 2 df the field strength? Or not necessarily?
Yes. It is kind of the same. Actually, you can decompose in this sense. You can decompose the Weil tensor into its electric and magnetic parts. Then you can compute the Ashtekar-Magnon-Das charges associated with these two pieces, and you will see that the electric part, the Ashtekar-Magnon-Das charge associated to the electric part, will give you the mass of the tau nut solution, but the magnetic one will give you something associated to the nut charge. What it is interesting is that since we are demanding, I will demand it now, that the F F nu lambda rho is equal to F tilde nu lambda rho. This condition implies the Einstein field equation. So I have a relation between the Weil tensor and the F. And once again, since we are demanding duality at the level of the F, and this is an Einstein space, it is equivalent to think this as a relation between the Weil tensor and its dual. And since the Weil tensor and its dual are equal, because we're imposing this, at the end of the day you will see that the electric and magnetic charges computed with whatever conserved charge method you want will be equal. So in this sense, it is sort of an anti-self dual diode, where the electric and magnetic sources are equivalent. So you can see this at the level of the conserved charges as well. It is not only a local property, it is also reflected at the global level. So if you demand this, okay, and I will finish with this. The solution you get is the anti-self dual tau nut solution, which is this metric. I have a lot to say about this solution, but I do not have time. We can discuss it in the coffee break if you guys are interested. This is the solution. It is the gravito analog of a dion in Maxwell theory. So it has an electric part and a magnetic part. The nut charge is associated to kind of a magnetic monopole. It has non-trivial topology, similar to the Dirac monopole. It also has a string, which is the gravitation analog of the Dirac string. It has non-trivial topology. There are a lot of nice things to say about this metric, but I do not have enough time. We can discuss it later. So thank you very much, guys.
We have time for one more question. Okay.
Yeah, so this thing that you have, air go from n to infinity.
Yes.
It's like you put a magnetic string between 0 and n or something like that.
All right. So, as you correctly said, the area coordinate tells us that the radial coordinate goes from n to infinity in general. But the string doesn't have, it's not related to the radial coordinate in this case. If you take this solution, you will see that the norm of the Euclidean time coordinate, so you take the gradient of this coordinate, take it squared, and you will see that there is a singularity with this norm. Or you can say it in another way, the inverse metric is singular not only at the position where f is equal to 0, because notice that f is equal to 0 at r equal to n. And at r equal to n, the metric degenerates into a point. So if you are close to r equal to n, this space looks topologically like the Euclidean four-dimensional space. However, there is a string at the origin of your space that it is located at theta equals 0 and theta equal pi. You can see that by computing the inverse metric of this one.
Oh.
And so this kind of singularity can be removed following the same trick that Dirac did for the magnetic monopole. So you perform a large gauge transformation, an improper gauge transformation, that of course will change the conserved charges of this metric. And so you move it. It is like redefining this coordinate. And so you can divide this metric into two patches, and then you glue it. But at the equator, you will see that there are, if you are in the Lorentzian, eliminating the Dirac string, the Wissner string, will induce closed time-like curves. So this is kind of pathological in the Lorentzian sense. And for a long time, the tau-NAT instanton was studied only in the Euclidean because it bears close resemblance with instantons in Germil's theory and blah, blah, blah. But recently, by 2016, Gerard Clement, Galston, and friends, they realized that actually you can leave there the Wissner string and nothing really worrisome will happen because the Wissner string is transparent for geodesic observers. So if you are free falling into the tau-NAT space, you won't see the Wissner string. However, other observers could see this string-like singularity. So it is a matter of research nowadays, what to do with the Wissner string. But in my opinion, nowadays the people is leaving there the Wissner string. Even you can perform the large diffuse just to move its position. This will induce a modification in the angular momentum of this solution, because in principle it is counter-rotate, both hemispheres are counter-rotating, so the angular momentum in principle cancels, and this has to do because the Wissner string is symmetrically distributed. But if you leave it only on one hemisphere instead of the other, you can do this by performing the large diffuse that I was mentioning. Then you will have that this solution has angular momentum induced by the net charge. So there are a lot of things to say about this, but going to your question in particular, the Wissner string has nothing to do with the radial dependence. It has to do with the theta dependence of this metric, because it becomes singular at theta equals 0 and theta equals pi. Because your metric, the inverse metric, is singular at those points.
Thank you.
Okay, so if there are no more questions, we thank Cristóbal again.